We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. Carta brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
So I am going to be talking about what happens when children get exposed to stimulation, not when they get deprived. And I'm going to focus particularly on language acquisition. I need to start by just saying a couple of words about what is a language and what would it mean to learn it. So in a very simplified fashion, what I want to say is that languages are combinatorial systems that involve figuring out what the units are at the lowest level sound segments, but then those combine. If you happen to be exposed to a sign language, it's hand shape or movement segments, but analogous to sound segments. Those get combined to form what are called morphemes, which is the smallest combinations of sound that have meaning. And morphemes get combined to form words, and words get combined to form phrases, and phrases get combined to form sentences. So the point here is that languages around the world are big combinatorial systems. And what you have to do when you're learning a language is to figure out what the combinatorial system of your particular language is. So I want to focus on two questions. One of them is what makes humans so incredibly good at learning languages? And the second is, why is this particularly true of very young children when adults are really typically better at everything than a young child, but young children are remarkably better at learning languages? So how do we understand that? So I want to start by talking about something that we have called statistical learning. This is work that I've done for a long period of time with Richard Aslan. And what we mean by statistical learning is that we and many other people have found that humans, especially children and including infants, are very, very good, remarkably adept at very rapid pattern learning. And we call it statistical learning because what we have suggested is that part of what they're doing when they listen to streams of sound, for example, I'm going to give you an example of this in a moment, is keeping track, absorbing naturally, that is, the brain is naturally absorbing from exposure the statistics of language input, by which I mean the brain naturally sucks up and keeps track of the frequencies of individual sounds and their occurrence in the streams that you expose us to, and the frequencies of co-occurrences of sounds that occur next to each other or even some distance away. And we use these statistics to acquire language. So what we have suggested is that part of the reason that we're so good at learning languages is because we have evolved a remarkable ability to acquire this kind of statistical information and use those statistics to construct the rules or the patterns of the languages that we're exposed to. We also, I'm going to show you in the second part of my talk, there are some internal inherent constraints and biases in the nature of this learning that change with maturation, and that's what I'm going to argue makes children better than adults at doing this kind of learning. We're really good at this when we're babies. We decline in our ability to do this over life. We all know you can still learn languages as adults, but you're not so great at it. So I want to illustrate with a problem that we started studying with Jenny Safran quite some time ago, which is the problem of word segmentation. And this is just an example. We've gone on to look at much more complicated problems, but I think it will help to give you a clear example of what I mean by statistical learning. So when you start being exposed to a language, the stream of speech that you get exposed to in any language of the world is actually continuous. There isn't any little white space in between the words the way there is when you look at print. So how do you figure out what the words are? That seems to be an early step that you have to figure out in order to learn the language. Which sequences of sounds form words? And what you see here is a waveform. Just showing you the high places here are, these places are lots of sound, high amplitude, and these places are less amplitude, less noise. And the red lines I've drawn are actually the places where you would hope that there would be some little white space. Those are the breaks between the words, but there are no breaks. So the point that I'm making here is the voice does get loud and soft as you listen to a sentence, for example, but it doesn't have anything to do with where the breaks between the words are. You're going to have to figure out what the words are and where the breaks between them are by some other method. So we did, quite some time ago, an experiment with Jenny Safran, looking at how you could figure this out. And this was originally based, as I'm going to show you in the next slide, on eons of linguistics. Linguists do this all the time. And if you look at a famous textbook, any famous textbook of linguistics, you'll find that what it tells linguists is when you listen to a new language, there's a bunch of statistical cues. They're usually called distributional information, not statistics, about how to tell what the units are. And the idea is that the words over a big body of speech are going to be the consistent sequences of sounds that you hear repeatedly. And the sequences that are across a word boundary are going to be much more changeable because words don't always occur in a fixed order. So what we suggested was maybe even babies, not just linguists, but maybe even babies, could use this pattern of distribution of sounds to figure out what the words are. And the idea in statistical terms is perhaps learners can use transitional probabilities, the likelihood that if you hear one particular syllable, it will be followed by another, to figure out what the words are. Now, I want to emphasize, this would be easy if you had a tape recorder and a computer, sort of. It's really, really not so easy if all you come with is you're a baby and you come with a brain. Somehow, large bodies of information would have to be stored in a relatively raw form, and then your brain would have to be busy doing these computations. And I'm not going to be able to give you the method by which the brain actually does this, but I want to show you that it does. So this is following Zelig Harris, 1955. Zelig Harris is my academic grandfather. And this was sort of his instruction to linguists, not to babies. The idea was if you hear a sequence like pretty baby or pretty flower over a body of speech, pretty would be sound sequences that you might hear recurrently, but tibbe would not. Tibbe would occur every once in a while when you happen to hear pretty followed by baby, but not on a consistent, high probability basis. So the question was, would you be able to figure this out without any meaning? So this is an experiment done with no meaning, no intonation, that is, no variation in the way that the speech is produced. It's all run together. It's run together in this particular experiment we did with adults, run together for 20 minutes. So this is an excruciatingly boring experiment to be in. And people listen to this, and then we ask them if they can identify the words. We don't expect that they'll do this consciously. We ask them if they can choose between the sequences that were the secret words and the ones that were across a word boundary.
Do ta ba tu ti boo do ta ba ba boo poo pa tu be do ta ba pi da boo ba boo poo pi da boo boo.
So that fascinating stream is what you hear. Secretly, because, let me go back to the list of words, because the syllables in this experiment are used in several words, there will be transitions, like between do and ta, that are very high frequency. And there will be sequences like ba to pa that will be low frequency, but it goes up and down because the syllables are used in different words, different numbers of words in different positions. So this is actually a piece of the stream shown at the bottom. And what you're seeing plotted here is the transitional probabilities. What's the probability that if you hear do, it's going to be followed by ta? And the important thing to notice is that the word boundaries are places of dips in the transitional probability, and the insides of words are relatively higher probabilities, because that's what it means to be a word. Part of what it means to be a word is that you hear these sequences recurrently. So our question was, if we exposed people to this incredibly boring stream of speech and paid them to listen, we paid them $7.50, lots of money. And then at the end, we gave them do ta ba versus boo pi da. Which one would they think sounded more familiar? That was the question we asked them. So here are the results for adults on the left and children, 5-year-old children on the right. This particular experiment we did while everybody was coloring, because we couldn't figure out how to get 5-year-olds to hold still. They weren't enticed by the 750. So everyone was coloring, and they heard these streams of speech, and then afterwards we asked them to judge, and this is the probability that they pick the word as compared with what's called the part word, the end of one word and the beginning of another. You can see that people absorb this information incredibly well. They do very quickly figure out which ones are the words. We also did this experiment with babies. So this is a drawing of a parent holding a baby. The parents don't get to listen to the speech, so they won't jigger the baby when the right answer comes up. But the babies are just sitting listening. We simplified the word structure. The babies listen for 2 minutes. And then we gave them the 2 alternative forced choice version in Babyland, which is light a little light over on the right, and babies will naturally look. You don't have to train them to do that. And then we would play a word or a part word, and they will get very bored when it's a word because those are the things they've learned. And they will show less looking time to the words than if it's a part word, which the fact that they discriminate suggests that they can do this as well. We also subsequently did it for things that are not language. So it turns out we're not just good at absorbing auditory patterns in language. We can do it for tone sequences. We can do it for visual patterns. We can do it for lots of things, including noise sequences. Those are the same kinds of statistical regularities built out of noises from the Mac. So people can learn this. It took a lot longer. This is not a very evolutionary, natural set of stimuli, but they can do it for those kinds of noise sequences as well. So in this line of work, our findings are that there's a mechanism for computing sequential patterns online extremely rapidly that we find in adults as well as 8-month-old babies. It's a remarkably complex ability, so I didn't tell you, like, how many syllables do you have to learn? How many probabilities do you have to be able to keep track of and compute in order to do this task? But it's a lot. And there were only 4 words in the baby experiment and 6 in the adult experiment. In our natural languages, we learn about 40,000 words. So to do this kind of task requires a lot of computation, but it does seem to be something that the human brain is extremely good at. And of course would be useful for learning complex patterns in a number of domains, but especially language. So what I've said so far is that humans, and including both babies and adults, are really good at doing these kinds of implicit learning outside of consciousness, but absorbing some of the patterned regularities that we get exposed to that enable us to learn language, we think. But what we've also found in subsequent experiments that I've been doing with many of my students is that we're very good at this when we're babies. We become not so great, although somewhat okay, at doing these kinds of tasks as we get older. And we've been looking especially at what is it that changes, what's so good about babies, what is it exactly that they're good at, and I want to just give you one example of the kinds of things we found. So, just to demonstrate that when we start young, we're actually better at learning languages. These are old data from Jackie Johnson and myself looking at second language learners of adults, and this is looking at groups of people whose families moved to the United States when they were at different ages. And what's being plotted here is their age of arrival in the United States. That's when their family moved. We didn't make them. They did it by themselves. But then we tested them when they had been here for 10 years. We gave them very simple tasks, judging sentences of English. And you can see that you get these enormous age effects. I want to also draw your attention to the fact that this was a 276-item task, and the bottom of my plot here is 200. So everybody's pretty good at it. I'm kind of exaggerating the age effects by the way I've plotted the data. But you get both age effects, and people in their adult life are still okay. But why are children better language learners than adults? And there are a couple of different ideas about this. One idea is that there might be a special linguistic ability, that is something special to language that diminishes with age, some kind of language faculty that gets worse as we get older. What we have suggested is that this complex pattern learning ability that I talked about really works especially well when we start with limited abilities, when we're very resource limited, when we don't have the ability to retain very, very complicated, detailed information about the speech stream, and when the statistics that we can compute are fairly simple. And so this is part of a set of hypotheses. I've called it less is more. Jeff Ellman, who was at UCSD and beloved by those of you who knew him, including me, called a similar hypothesis starting small. And the idea is perhaps it's because of starting small at these abilities that we actually can focus on the most prominent statistical patterns and then acquire gradually those that are less prominent, less regular. And I want to show you some experiments that we've done to look at this hypothesis. These are data that are actually natural language data looking at a child, Simon, who was a deaf child whose parents were late learners of the language that he was learning. He was learning American Sign Language, but we brought this into the lab and we can show the same phenomena in spoken languages. And the idea here is that Simon learned the language from his mom and dad, who made lots of mistakes, and they were very inconsistent. He didn't actually know anybody who used this language other than his mom and dad. And yet you can see that on a task when he was 9, he was better than his parents. And so we got interested in trying to understand this phenomenon and brought it into a laboratory experiment. And what we think is going on that I want to show you in experimental data is that when you give young children inconsistent input, they find the thing that's the more consistent out of a kind of noisy exposure, and they form a very strong rule about the more consistent things that happen. And they don't learn the mistakes. They don't learn the occasional regularities. They really regularize or exaggerate those things that are somewhat consistent in the input that they receive. Adults don't do this. Adults learn it all. They probability match, and that's not very useful at learning a language. So we've done a bunch of experiments with children and adults, giving them inconsistent input in the lab. And these are miniature languages. The children are 5 and 6. And we give them a variety of exposure sessions, but they get little words after nouns, ka and po, that are on purpose inconsistent. So I want to just quickly show you the paradigm. We show them little movies that they hear, and they hear sentences that are in an artificial language. And they see things like the bee headbutting the giraffe. These are just stills. And then after that, they see novel films. They get the beginning of the sentence, which in this case is a verb, and they have to speak the language after 5 days of exposure. And everything's very regular, but ka and po occur very inconsistently. In the first experiment that I want to show you, they get ka 67% of the time after a noun at random, and 33% they hear po. And if you do this with adults, you can see that they perfectly reproduce the inconsistency. These are actually the data. Adults produce 67% ka and 33% po. Here's what 5-year-old children do. These are the adult data moved over, and this is the children. Children do 90% ka and 10% po. So they find the thing that's the more regular and do it more often. We did this also with a 40% condition where they're only hearing ka 40% of the time, po 20, and the rest all scatter. You can see that adults, again, do 40% when they're presented with 40%. Here's what kids do. The thing they hear 40% of the time, they still do almost all the time. So what the kids are doing is regularizing even inconsistency. They're doing statistical learning in a funny way. They're changing the statistics into things that are very regular that in linguistics we call rules. And adults are reproducing the noisy, crummy statistics that they get exposed to, which is a skill in and of itself, but not very good for learning languages. So let me turn to my conclusions. We think that in many experiments, I've just given you one example, that statistical learning is a very important part of language acquisition. Humans are remarkably sensitive to a variety of statistics that reflect linguistic distribution of elements in the speech stream. And they use these statistics to acquire the rules and structures of natural languages. But what I want to emphasize is statistical learning is not veridical, at least not in children. It's not just learning whatever's in the input. That is not what we do when we learn a language. Statistical learning is also not the same over age and maturation. Children learn somewhat differently than adults. They make inconsistent usages more regular. We found this in about 10 experiments now. And they also favor certain types of patterns over others. So we've also done experiments where we give them things that are like what happens in languages of the world and things that are like not like what happens over languages of the world. And they change the languages that they get exposed to into something more like real languages. So there are clearly biases about certain kinds of patterns that show up in the laboratory that also seem to shape languages of the world. So we think these biases and constraints on learning may help to shape languages over generations. Thank you.